For the last 10 years, modern AI has been built on top of a single architectural assumption. It's an idea so foundational that it stopped being a choice and, well, it just became infrastructure. It works, it scales, and until very recently, it was pretty much considered the only reliable way forward.
Right. You heard that correctly. A full decade. We're talking everything from open source models all the way up to the massive frontier models. They are all built on this same core idea. A blueprint that became so successful, it became an unquestioned truth.
Because a new paper just published by a lab called DeepSeek effectively dismantles that assumption. They've engineered a method that bypasses the information bottlenecks that are inherent in all of today's large language models. And if this new architecture holds up, it means the standard way of building these things is now obsolete.
So to really understand the scale of this breakthrough, we first have to rewind a bit. We need to look at the original problem that this decade-old assumption was actually created to solve. It all started with a foundational flaw in early neural networks.
You see, in the early days of deep learning, researchers kept hitting a wall. The deeper they made their networks, the more layers they added, the worse they performed. They just stopped learning. The signal that tells the model how to correct its mistakes, the gradient, would just fade away as it traveled back through the layers. It was like trying to whisper a secret down the very, very long line of people. By the time it got to the end, the message was just gone. The fix that saved the entire field was honestly brilliantly simple. It was a clever shortcut called a residual connection. It basically created an express lane for the information, allowing the signal to skip over layers and keep its strength. And that single idea is what made training incredibly deep, powerful networks possible. But, and this is the crucial part, that elegant solution created a brand new, much more subtle problem, a kind of stable bottleneck that has been hiding in plain sight ever since.
So these residual connections created this perfectly stable, predictable highway for information to travel on. The learning signal could flow from the end of the network all the way to the beginning without getting garbled or lost. Stability was the key, and this architecture guaranteed it.
And, because it worked so incredibly well, it just became the default. It became infrastructure. But that stability came with a hidden cost. It forced all the complex, high-dimensional information being processed by the model through a single, narrow information stream. Think of it like trying to push all the traffic of a major city through one single-lane tunnel. It works, but it's a massive choke point. Now, the obvious fix, of course, is to just build more tunnels to widen the path. Researchers tried this with something called hyperconnections, which allow for multiple information streams. But every time they tried it, the result was the same: a catastrophic collapse. And here's the dilemma in a nutshell. On one side, you have residual connections, a single stream, limited capacity, but totally stable and predictable. On the other, you've got hyperconnections, multiple streams, massive capacity, but dangerously unstable and prone to sudden, complete failure during training. This quote from the paper just says it all. Everything still looks fine until suddenly it isn't. And that's exactly what would happen. You could be training a model for weeks, spending hundreds of thousands of dollars on compute. All the metrics look perfect. The model is learning. And then, out of nowhere, boom, the whole thing just numerically explodes. The training run is a total loss. And because of that risk, the idea was basically abandoned for any serious large-scale work. When a single training run costs millions of dollars and takes months, you just can't afford to bet on an architecture that might catastrophically fail right at the finish line. It's just too risky. So that brings us to the DeepSeek breakthrough. They figured out how to get the huge capacity of those hyperconnections, but with the guaranteed stability of residual connections, they essentially created a mathematical lock. They call it Manifold Constrained Hyperconnections, or MHC. Now, the name's a bit of a mouthful, but the concept is really elegant. It lets the model use all those parallel information streams, but it enforces a very strict mathematical rule that guarantees they can't spiral out of control. It gets the best of both worlds. So here's how that lock works. Inside the model, information can be shifted around between all the different streams. It can be mixed, blended, redistributed, but, and this is the absolute key, the total signal strength across all of those streams combined has to remain perfectly constant. The energy of the signal can't be amplified, and it can't be dampened. It has to be preserved. And the beautiful part is, this isn't something they just hope for or carefully tune. The stability is mathematically guaranteed by the very structure of the operation, using specific algorithms. It's not a guess.
It's a proof.
Okay, so the theory is elegant, but does it actually deliver in the real world? Let's take a look at the proof in the performance. On a notoriously difficult mathematical reasoning benchmark called GSM-8K, a standard model scores about 46.7. The MHC model, with the exact same number of parameters and training data, jumps all the way to 53.8. I mean, that is a huge leap in pure reasoning capability just from changing the architecture. And they didn't just stop at the theory. They actually did the hard engineering to make it work efficiently. This meant building custom GPU software and new scheduling systems, all to get around a fundamental bottleneck in AI hardware, known as the memory wall. And here are the results of that engineering. By implementing this new architecture, they increased the model's internal bandwidths, its ability to move data around inside itself, by 400%, a 4x increase in its internal workspace. But here's the truly stunning number. That massive 400% gain in data capacity cost them only a 6.7% increase in total training time. That kind of trade-off, getting that much of an upgrade for that little overhead, is almost unheard of. The efficiency is just off the charts. So what does this all add up to? If we zoom out, we can start to see what this means strategically, not just for DeepSeek, but for the entire AI landscape. This is the new reality. I think this quote from Wei Sun, a principal analyst at Counterpoint Research, really nails it. He says this isn't just about a new model. It's a statement of DeepSeek's internal capabilities. By proving they can redesign the entire AI training stack from the ground up, they're signaling to the world that the normal rules about compute constraints, well, they don't apply. They'll just engineer their way around them. And that really leaves us with one final, pretty unsettling question. If a foundational assumption about AI architecture, one that had stood for an entire decade, just turned out to be a major limitation, what other solved problems are we all taking for granted that are actually just the next hidden bottleneck?